Henry's law. Class, we've already discussed Raoult's law, that was solution of two liquids. Then we discussed qualitative properties, solution of non-volatile solute and liquid. Now, there is a third topic, that is Henry's law, which is formed due to solution of gas plus liquid. When the gas is being dissolved in the liquid, what does he say? He simply said, more the pressure applied by the gas on the surface of the liquid. I repeat again, more the pressure applied by the gas on the surface of the liquid, more the solubility of the gas in the liquid. As you put more pressure of the gas on the surface of the liquid, more number of molecules will be bouncing on the surface of the liquid, and hence more will be the solubility. So, in the next step, we can find out a formula. He simply said partial pressure of the gas is directly proportional to solubility of the gas, that is number of moles of the gas. Sorry, mole fraction of the gas. Partial pressure of the gas is directly proportional to mole fraction of the gas. Higher the mole fraction of the gas in the liquid, more the solubility. In the next step, you can just find out pH, Pg equals to KH into Ng upon Ng plus Nl. Class, what is KH? Okay, constant of proportionality, but also called Henry's constant. Henry's constant. And mole fraction, I will already discuss with you. Mole fraction is always number of moles of the component upon total number of moles. So Xg is Ng upon G represents gas, L represents liquid. So Xg is number of the moles of the gas upon total moles, and total moles your number of the moles of the gas and number of moles of the liquid. But number of moles of gas, okay, solubility of the gas is very less in liquid or in water. So we can say that number of moles of gas is much less than number of some liquid. Therefore, Ng is ignored in denominator. So the formula becomes Pg equals to Kh into Ng upon Nl. Class, Henry's law, for Henry's law, we will be always using this formula. Numerical is already on the board. The numerical says find KH, remember Henry's constant, for 0.195 molar solution of H2S, you all know H2S is a gas, in water at STP. I repeat, find Henry's constant for 0.195 molar solution of H2S in water at STP. So we'll use Henry's law, Pg equals to KH into Ng upon Nl. Class, remember one thing, this is a ratio, no? Number divided by number, so it's a ratio, so it does not have any unit. So whatever unit of pressure you are writing here, the same unit will be of Henry's constant. Class, I've already told you that at STP the pressure is 1 atm or 1 bar. If you are putting 1 atm, then answer will come in atm. If you are putting 1 bar, then answer will come in bar. So let us take here pressure 1 atm. So partial pressure of the gas is 1 atm. Number of moles of gas is 0.195. But what is Nl? Class, now you have to remember your molarity expression. What was the molarity expression? Molarity expression was, how do you define molarity? Number of moles of solute present per kg of solvent. So what is solvent here? Water. So what is the weight here? 1 kg. So what does it mean? It means 0.195 moles in 1 kg H2O. So pressure of the gas 1 atm. KH we are going to calculate. Number of moles of gas 0.195, and number of moles of liquid, weight is 1000 gram, and it should be divided by its molecular weight. So that gives you 55.55. So I write again 1 equals to KH into 0.195 upon 1000 by 18 gives you 55.55. Next step, cross multiply 55.55 divided by 0.195 equals to KH. 0.87. And what will be the unit? ATM. So unit will be ATM. So class, let also complete your third topic, that solubility of a gas in an ideal and non-ideal solution, and it is meant for two liquids. Class, as I already told you that solution of two liquids is governed by Raoult's law. So what is ideal and what is non-ideal solution? Ideal solution which obeys Raoult's law at any given concentration. Non-ideal solution which does not obey Raoult's law at any given concentration. Now class, we are going to understand behavior of ideal solution when two solutions are being mixed. Friends, the concept is very, very important, so I want you to focus on the graph itself. See, XA, what is XA? XA is mole fraction of A. XB, mole fraction of B. So at the origin, mole fraction of A is 1. So mole fraction of B liquid is 0. And since only liquid A is present here, so the vapor pressure corresponds to PA0. And since here only mole fraction of B is 1, so only B is present, so therefore vapor pressure of B is PV0. I repeat again, mole fraction of mole fraction of liquid A is 1, means only liquid A is there, so the vapor pressure corresponds to PA0. And here mole fraction of B is 1, so vapor pressure corresponds to PV0. Now class, what we are going to do? We are going to mix these two solutions. Let us see here. Mole fraction of A is 1 here. So now we are going to add B to liquid A. I repeat, we are going to add liquid B to liquid A. And as we start dissolving B in A, then what is going to happen? Mole fraction of A will go on decreasing. So let us take 0.9, 0.8, 0.7, 0.6 mole fraction of A. And you see the vapor pressure of the liquid A goes on decreasing. Why it goes on decreasing? I can give you an example over here. See the board. Let us take PA0 equals to 100 mmHg. So when there was only liquid A, the vapor pressure was corresponding to PA0, its original vapor pressure. And as soon as you start adding B in liquid A, the mole fraction goes on decreasing because now B is also present in the solution. So the mole fraction of A, let us assume that descends to 0.9. So then what will the pressure of A? 0.9 multiplied by 100 gives you 90. Put some more liquid B, again the mole fraction of A will decrease. Now let us take 0.8 into 100, that gives you 80. Again you put liquid A, liquid B in liquid A, again mole fraction of A goes on decreasing, giving you values 70. So when liquid A was there, the vapor pressure was corresponding to PA0, and when you are pouring liquid B in liquid A, mole fraction of A goes on decreasing, and hence its vapor pressure also goes on decreasing. See, 100, 90, 80, 70, 60, 50, 40 and so on. Similarly here liquid B was present, and in the same way it was corresponding to PV0, and if you put liquid A in liquid B, the mole fraction of B goes on decreasing here, and you see the vapor pressure of B also goes on decreasing. And now I am going to join these two lines, PA0 and PV0. So this line, this curve indicates vapor pressure of solution at any given concentration. Let us take here, if we want to find out the vapor pressure of solution, not liquid A and liquid B, vapor pressure of solution, let us take if mole fraction of A is 0.6, then obviously mole fraction of B will be 0.4, because you know mole fraction of A and mole fraction of B whenever added gives you value 1. So you see, I will just join this line to here. So here, this is the vapor pressure of solution when mole fraction of A is 1 and when mole fraction of A is 0.6 and mole fraction of B is 0.4. PA naught and PB naught can never be equal because these are two different liquids and they have different vapor pressure. That's why PA naught is greater than PB naught. You can also make it PA naught less than PB naught. But always remember the PA naught and PB naught can never be equal because these are two different liquids. So class, this was the curve of ideal solution. What are the salient features? I am going to write here. Salient feature number 1 obeys Raoult's law. So what was Raoult's law? PA will be always equal to XA into PA naught and PB will be always equal to XP into PB naught. Number 2, delta V mixing. Delta V mixing means when we add two liquids, 10 ml of liquid A and 10 ml of liquid B, we get only 20 ml, so delta V mixing is 0. There is no change in volume. And third, delta H mix is also 0. What is delta H? Delta is your enthalpy change whenever liquid A and liquid B, and if they are following ideal solution, if you are going to mix them, the reaction is neither exothermic nor endothermic, neither heat is given out nor heat is taken in. So this was the curve for ideal solution. In class, in the next topic, we are going to take non-ideal solution, and it has two types: solution showing positive deviation and solution showing negative deviation. So now the topic becomes non-ideal solution showing positive deviation. Let me up. Class, dot this straight line, bold line indicates ideal behavior just to study. And I am going to show positive deviation on this curve. So class, this is the curve for non-ideal solution showing positive deviation. What are the salient features here? As you know very well, it is non-ideal solution. They will never follow Raoult's law. What is the condition over here? Let us see. Condition is, if interaction of A dot A and B dot B, what does it mean? It means if the bond between liquid A and the bond between liquid B is more than AB interactions. It means that A has more tendency to remain itself A, B has more tendency to remain itself B, then they form solution. So solution forming tendency is less. And if solution forming tendency is less, previously they were going to the solution, so vapor pressure of solution was decreasing. But here A and B, they do not have any tendency to form solution because interaction of A is greater, B interaction greater than AB interaction. Therefore solution forming tendency is less. In class, if solution forming tendency is less, they will try to remain as A and B. So previously the vapor pressure of solution was less, but here since they are not going into the solution, but not to the more extent, therefore their original vapor pressure will be always, you see, more than expected. When they were ideal solution, their vapor pressure curve was this. Since their solution forming tendency is less, therefore the vapor pressure will be always more than expected. Similarly for B also, vapor pressure of B will be also more than expected. Hence, PA will be greater than XA into PA naught. PB will be greater than XB into PB naught. Therefore, PS will be always greater than PA plus PB. So class, at any given composition we find, you see this was the ideal curve, but at any given composition we find that the vapor pressure of solution curve is always above PA naught and PV naught. So at any given composition of A and B, the vapor pressure curve of the solution will be always above than the ideal behavior. That's why we call it positive deviation. So this was salient feature number 1. Second, delta V mix. Whenever we are going to mix these two liquids, delta V mix will be also positive. I repeat again, class. Since solution forming tendency is less, therefore A and liquid B, they will be trying to remain apart as far as possible. And if they try to remain as far as possible, then intermolecular distance will increase between A and B. And if the intermolecular distance increases between A and B, then obviously volume is also going to increase. Third feature is delta H mix equals to positive. Means dissolution is endothermic. Class, why the dissolution is endothermic? I repeat again, since interaction between A and BB were very high, solution forming tendency was less. But if we heat both the liquids, then the bond breaks and ultimately they go into the solution. Therefore, endothermic, the dissolution is always endothermic. Dissolution will take place at a very high temperature, and if it takes place at a very high temperature, dissolution becomes endothermic. For non-ideal solution showing negative deviation, this is the curve. Bold line indicates ideal behavior and dotted line indicates negative deviation. In the last curve, we found that this curve was lying above the ideal solution curve, so they were showing positive deviation. But in this case, it is lying below the curve, means showing negative deviation. Why they show negative deviation? The reason is here. If interaction of A and BB is less than AB interaction, means the bond between AA and bond between BB is very weak, then the solution forming tendency is very high. So if solution forming tendency is very high, they will go into the solution more than expected. And if they go into the solution more than expected, then their vapor pressure will be also less than expected. It was supposed to be here, but since solution forming tendency is more, so they will go into the solution in a very large amount, and hence the vapor pressure of the solution, vapor pressure of individual liquids will be always less than expected. And hence, at any given point of time or any given composition, we find that vapor pressure of the solution is always less than expected. So, partial pressure of A will be less than XA into PA naught. Partial pressure of B will be again less than XB into PB naught. Therefore, vapor pressure of the solution will be always less than PA plus PB. Therefore, the solution is showing negative deviation. Coming to the salient feature number 2, which says that delta V mix equals to negative. Class, in the previous one, since A and BB interaction were more than AB interaction, so solution forming tendency was less. They were trying to remain as far as possible. But in this case, since solution forming tendency is very high, so they will come very close to each other. And ultimately, when they come very close to each other, intermolecular distance will decrease. And if intermolecular distance will decrease, then definitely volume is also going to decrease. And the last topic, that delta H mix equals to negative, means the dissolution is exothermic. The reason is that since solution forming tendency is spontaneous, they want to form solution more than expected, so the reaction is spontaneous, and we all know from thermodynamics, if a reaction is spontaneous, then delta H, that is the enthalpy change, should be always negative. So class, we have studied 3 solutions: ideal solution and non-ideal solution showing positive deviation, and non-ideal solution showing negative deviation. Thing remains more, that is your azeotrophs. So what are azeotrophs? Azeotrophs are solutions of fixed composition in vapor phase as well as in solution phase. Hence, they cannot be fractionally distilled. We cannot separate them. Liquid A and liquid B cannot be separated, and they are also called constant boiling mixture. In board examination, short notes on azeotrophs are being asked of 2 marks. This entire explanation of azeotrophs. That what is, again I repeat, what is azeotrophs? Azeotrophs are solutions of fixed composition in vapor phase as well as in solution phase. Hence, they cannot be fractionally distilled, and they boil at constant temperature, and hence they are also called constant boiling mixture. So class, that completes my entire solution chapter.